Physics Lecture 6, Electrostatics and Magnetism. Before we start talking about electrostatics proper, let's go over a couple fundamentals, starting first and foremost with charges. If you remember from the general chemistry module, you'll know what a proton and electron are, so we won't go into too much detail about those. Attractive forces are when oppositely charged objects interact. Repulsive is when similar charges interact. So when you have two opposite charges, you will notice that they will be attracted to each other. The opposite is true when you're dealing with like charges. The coulomb is the SI fundamental unit of charge. This should be provided to you on test day, but for unit purposes during your calculations, you may want to just memorize this. I am sure many of you have heard about insulators and conductors before, but let's briefly go over them. Insulators are any material that will not easily distribute a charge over its surface, nor transfer a charge. Because of this usually tends to be nonmetals, and they're often used to ground and prevent the spread of charge. Conductors, on the converse, are easy to distribute the charge over its surface and transfer charge well. They tend to be metals, and they're used to transfer current or charges. Now that we've covered some basics, let's go into electrostatics proper, starting with Coulomb's law. This quantifies the magnitude of the electrostatic force between two charges. Now, you'll notice that with a lot of these equations, they look a lot like the ones for gravity and gravitational potential. If you would like, it may be a good idea to clump these two together when you're studying. The electric field is the influence that a source charge has on its surroundings and other charges. The equation is listed below. Field lines are useful in the sense that they imagine how positive charges would move through an area. They point away from positive charges, since the positive charges move in that direction, and they point towards negative charges, because positive charges will go to negatives. So if we were to draw this out, positive charges will be depicted with field lines going away from it, like so. Negative charges, we'll have them going towards them, like this. Electrical potential energy is listed below. Now, again, this looks an awful lot like gravitational potential energy, and the principles are very similar between the two. So it really would help you if you were to clump these together while you were studying. With respect to work, we can state that work equals the change in potential energy. And running through the calculation, you will end up with the same potential energy equation listed above. Electrical potential is measured in volts, V, and the potential difference is noted as the change in potential. This can also be equated to work over charge. Equipotential lines are lines in which the potential is the same at every point. Think of it as an elevation map. Those of you that have seen elevation maps before will notice it looks something like this. As the levels get lower and lower, it signifies the same elevation. Think of this as an equipotential line for elevation. Electric equipotential lines in this sense are where the potential is the same. So any point along these lines will have the same potential as any other point. Dipoles. This is the influence two charges of equal and opposite charge have on objects some distance away from them. Math is listed below. It's helpful to have these under your belt when you're going through. You probably will be asked to calculate these during your test. An example is listed below, but there's another possible setup for this. You could also have charges listed as in this area, in this layout. you may see charges listed like so on test day as well, so make sure you're aware. Now that we've had a brief overview of electrostatics, let's go into the second portion of our lecture, which is magnetism. Starting first, let's talk about magnetic materials. Diamagnetic materials, as the name would suggest, are made of atoms with no unpaired electrons. Because of this, they have no net magnetic field, making them weakly antimagnetic. Paramagnetic materials are made of atoms with unpaired electrons. They will become weakly magnetized in the presence of an external magnetic field because those unpaired electrons will move and line up with that magnetic field. Ferromagnetic materials are similar to paramagnetic materials, but they will become strongly magnetized in the presence of an external magnetic field. So think of this as a paramagnetic material on steroids. What is a magnetic field, though? Magnetic fields are caused by the movement of charges. Their SI unit is the Tesla, but for smaller fields, we'll use the Gauss. The Lorentz force is the sum of this electrostatic and magnetic force acting on a body. Note that any movement and any moving charge is going to create some sort of magnetic field. There are two magnetic field equations, and it depends on the charge and how it's moving. For a long straight wire with the charge moving, this is how you calculate it. And for this sort of a straight wire, you'll notice that the magnetic field generally does something like this. The other case is for a circular loop, something that looks like this, with the current moving through. So we've got I, which is our current here, I, as it moves through. You'll notice that as I moves, the magnetic field will spin around. Make sure you have these two under your belt and know the distinction between the two. Depending on the system that you're dealing with, you'll have to use one or the other come test day. Magnetic force on a moving charge. This is the force applied to a moving charge by a magnetic force, and it's noted below. To determine the direction of the magnetic force on the charge, you have to use the right-hand rule. Remember earlier, we talked about the right-hand rule. This is one of the other applications for the right-hand rule. So, to orient the right-hand rule in this situation, you have to take your thumb, your right-hand thumb, and point it in the direction of the velocity vector. Then, your fingers will be placed in the magnetic field lines. Your palm points in the direction of the force vector for a positive charge. Your backhand, on the other hand, will point to the direction for a negative charge. Finally, let's talk about force on a current carrying wire. In the diagram below, you'll notice that the right-hand rule has been applied for you, but it is the same, and it curls around the wire, as you can see. The force is characterized by ILB sine theta, or current times the length of the wire times the magnitude of the magnetic field times the angle between L and B. So as you can see, there is a lot of similarities between electrostatics and magnetism as earlier lectures. Keep these in mind when you're studying, and make sure you have a good grasp of electrostatics and magnetisms come test day. These will be topics you will be tested on, and without a good understanding of these materials, you will not be able to understand and move forward. Please join us in the next lecture as we go into circuits.